welcome back. It's True again with another Cafe Yocto episode featuring the phyCORE-AM64x system-on module. If you joined us in our last episode, you caught me running through the Build the BSP guide, which looks like this here in the developer wiki. We're going to kind of piggyback on that topic and talk about another thing that we can do here with the Yocto project and the BoardSport package, and that is compiling your own SDK, standalone SDKs, which include a cross-compilation toolchain, which essentially is going to enable you to get an application development team iterating and working on application level software rather than the BoardSport package and Linux kernel, things like this. The reason is you'd want to kind of separate those two, the application layer development from everything in the BoardSport package, is the Yocto project is just really cumbersome. It's not really intended to iterate on those individual components of an SD card image. And so this cross-compilation toolchain and that's within the SDK will enable you to iterate on those things separately, and then you could hand off that finalized application binary back to your Yocto integrator, incorporate that into your production-ready software image, and then flash that to your system at the time of manufacturing. So separating those two in terms of development is going to be a lot. It's going to facilitate a lot more efficient work, in my opinion. So here at the end of the guide, we walked through this last time. Here at the end, we just talk about here building the SDK. So this is going to be custom to the SD card image that you've built. So specific kernel headers for your kernel version. So if you're iterating on your Linux kernel, you're going to want to rebuild your own SDK installer. You do that with this command here. And we could go ahead and do that from here in this build environment that I've already sourced before hitting record. So this should look familiar if you saw our last video. Go ahead and check that out if it's not looking familiar. We could run that. Just imagine that I did. I'm just going to pretend that I did. I have already ran it. And when you do that, it'll deploy the SDK installer here to deploy SDK. We can see here that this is the actual .sh bash script. This is the installer itself. You can also check out the manifest files here that are going to outline everything that's included in the support that's included here in the installer upon installation. You can see that there's support for both your target and host machines. So this is everything you need here. This is a standalone SDK installer to get started with cross-compilation. We could copy this file to our local Linux environment or run it from here directly, depending on your how you're building your BSPs and where you're hosting your build machine. What I'm doing, if you caught my setup explanation in the last video, so I kind of host or access a cloud-based build machine, so I would have to transfer this guy to my local virtual machine where I actually can access SD cards, and then I could develop my applications and transfer them to the card. We're going to do that a little bit to get together, just kind of getting into running that installer. So here, what I want to show here in the install SDK guide, I just kind of showed that you could build it yourself. You can also just grab the pre-built one at phytech hosts. You're going to want to build your own if you're doing heavy kernel modifications. But you can just grab this pre-built one with this command. Again, pretend that I did that. I actually have it here just to save some time in the recording. And so I can actually give that executable permissions with this command. And then you'll have to make a directory to install this guy. Note here, I've already done this, but I'm just kind of walking through all the steps. So once you've created the SDK directory, you can create this anywhere. Just make sure it's in a location where you have permissions for whatever user you're logged into as. So anything here in the home directory is a good option. So I've just made this home/temp. Anyway, navigate there. And let's get the absolute, or the full absolute path to that directory. We're going to need that here when we invoke the installer. So now we can go ahead and do that, and then we would give the install path here when prompted. Again, we're going to pretend that I already did that because I have utilized this SDK2 directory. Now what's going on in here? There's a number of files. The important one that we really want is this guy. So this is going to have the setup for your cross-compilation environment, specifically for targeting the ARM 64-bit architecture. And then this sysroots directory, this is going to include all the headers, the library support, and then the cross-compiler toolchain as well. We can get access to that just by sourcing this environment setup script. So to showcase what that looks like when you do that, we're going to first look at my default shell environment. So these are all these variables that are exported by default whenever I create a new shell. What I'm going to do is source the environment setup, like so. And now, when I print env, I'm going to have quite a lot, actually a lot more environment variables exported. And so some of the ones that I want to try to draw attention to, just to give a quick overview of the kind of stuff that's here. Looking for it here. Arch equals ARM64. This is automatically exported. This guy, this Arch direct environment variable, this is typically used in software projects that are supported in multiple architectures. The Linux kernel and the U-boot bootloader are good examples of those. You would need to export this exact variable in this way in order to compile the Linux kernel in a standalone cross-compilation environment independent of Yocto. So this variable is pretty critical there for those sorts of packages or image components for your software image. The one that we're really going to use today is, this is another good one used in the Linux kernel. Now, rather than cross-compile, I'm going to direct our attention to, if I can find it just with my eyeballs, this guy, CC. So this is very much similar to that cross-compile one. However, this guy has the sysroots. Essentially, it's a command line option for this command that's going to point to the directory containing all of our libraries, our headers, things of that nature. So what we can do here is we can leverage CC to compile things in a cross-compilation context. Oh man, I should write a script. Okay, so in the previous videos, we've talked about compiling Hello World and Blink. What we did was we used GCC, however, it was on the target, so that was a native cross-compiler. If I'm going to try to build something here in my host machine, which has way more resources, more processing cores, more RAM than your typical embedded system, so I would want to compile it here in my host machine, but it's a different architecture. And we could prove that by checking the native compiler's target configuration here. It's going to target x86. So if I compile things in the host machine with GCC, I will get a binary that will not work on the SOM. They're different architectures. So what I need to do is invoke that cross-compiler, like so. And we could see here now with that variable that's already exported, I can easily run the cross-compiler including the SDK installed, and we can confirm the target is going to be ARM64-bit. So if I compile things with this environment variable, I will create a binary here in the host machine that won't work on the host machine but will run on the SOM. So this, when we want to cross-compile things, you just have to use this variable. So let's walk through a quick example, kind of building on what we've done in the past. We're just going to do that hello world again. However, we're going to kind of go out of this section. Talks a little bit about the CC variable I just mentioned. Let me go ahead and grab that hello world code again. And I'm going to create a file. Oops. What's going on? There we go. And let's go ahead and compile it. Now, if I use this file command, I can just double check, hey, it looks like it's compiled for ARM64-bit architecture. So if I try to run this here on my host, it will not work. You get this format error. We can go ahead and transfer this over to the board. Let me go ahead and do that together with you. So we got this. Now there's a number of ways we can get the binary onto here, right? We could power this off, remove the SD card, put that binary onto the SD card, boot this back up with it, and then once we boot into Linux, we'll have that file system mounted, so we could just grab that file then at runtime, or use USB boot media, or what am I saying? USB removable media, like a thumb drive, or we could use the network, and I'm just going to go ahead and use that here as my as for my example. So plug that in, and let's hop back over to Server Console. We can see that the link should just come up automatically. DHCP is enabled on this interface by default. So here's this IP address for the device on my local area network. Let me grab that. And now I can use this secure copy command. So this copies files over a shell SSH tunnel, essentially. So it's very secure. I'm going to copy it like this. I'm going to go to root at that address, and then to the directory after the colon there. So if I do this, oh yeah, do it. We can see this hello files here, and I can go ahead and run it. Hello world, and it's working. So that's how we could go ahead and start working in a cross-compilation environment using the Yocto project to generate an SDK installer.
Thanks for watching video number 4 in our series, and stay tuned for the final video of the series tomorrow. Once again, don't forget to like and subscribe to our channel because we will be doing more series like this in the future. Thank you so much, and see you tomorrow.